So in the last couple of videos, we've reviewed what happens in a flat mirror and how we can get a virtual image. Now we want to curve the mirror. And so let me do a screen share and show you what happens when we have a curved mirror. Okay, so first we need to draw a mirror, and we're going to draw one that's spherical. All right, now it's going to look circular when we kind of look at the cross section in 2 dimensions, but I'm going to start my mirror right. Whoops, that was the eraser, not the pen. Let me undo what I just did there and pick up my pen. And I'm going to have the mirror have a start right there, and the center of curvature is going to be right over here. Right, so you can see on my axis it's about 4 units long. Now, if I'm going to keep the same radius, by the time I go up a unit, I'll have curved something like that. And if I keep going up, I probably should curve about like that. So if I were to draw some radial lines, they would look something like this, and those should all be the same length. And then I should come down and be able to do the same thing down here and keep on sketching, and I'd have some radial lines that look like this. Actually probably came around a little bit too tightly here at the end. I probably draw this in. Whoops, that's my eraser again. Probably something more like that. So I would have these radial lines in there, okay? Now those radial lines are important because if light rays, which I'll draw in red, are coming in and hitting the mirror, they have an angle of incidence. Those radial lines are the normal lines to the mirror because the radius of a circle or sphere is always going to be perpendicular to the surface of the sphere. So those radial lines are the normal, and therefore the law of reflection says that the ray that bounces off of the mirror should head in the same direction, and it'll just keep on going like that. All right. Now, if we take another ray and it comes in down here at the bottom of the mirror and hits there, we have an angle of incidence, and we should draw at an angle of reflection that looks to be the same in size, and it gives me a ray that looks something like that. And you can see those 2 rays met at a point. Now, if we draw more rays of light coming in, let me draw a ray of light coming in right here. If that bounces out so that its angle of reflection equals its angle of incidence, it will hit at the same spot. Now, it turned out if this is a spherical mirror, they don't hit quite at the same spot if they're not at the same distance away from we call that middle line, the optical axis. Okay, so let me fill that in. Right here is the optical axis. It's the axis of symmetry of the mirror. All right. So as the rays that are above and below the optical axis by the same amount will in fact meet at the same point. The other rays will almost meet at the same point. All right. Now that's true if this is a spherical shape. Now I've only shown it in 2 dimensions, but we could go left and right as we come in and out of the page or screen and see the same kind of relationship. So this is spherical. If, on the other hand, this was parabolic, we saw this back in your sophomore year, hopefully, that the properties of a parabola are that parallel rays coming in would go exactly through a single point called the focal point. So if it were parabolic, it would be perfect. Parabolic mirrors are expensive to make, though, whereas spherical mirrors are actually fairly cheap to make because to shape it, you just put it on the outside of a ball. And you can grind, you have to grind mirrors to form them. So you can take a ball and you can grind it into a surface and create a spherical depression. And then you can silver that and you have a mirror. Whereas it's a bit difficult to get a parabolic mirror because you can't just grind a piece of a parabola. You can't just shift it around and grind it the way you can with a sphere. So most mirrors, except for really expensive ones, are spherical, but they're almost parabolic as long as we don't curve too far. Turns out if we curve really far out here, light rays coming in, I'll do one in blue, a light ray coming in if it reflects at the same angle that it hit, it ends up hitting, crossing somewhere in front of that focal point. Might even hit the mirror again and bounce out. So it doesn't quite pass through the focal point. It still gathers towards the focal point, but it doesn't pass through the focal point. All right, so this is a mirror in the shape of this. This is a concave mirror. All right, and it will focus the light, the light rays, so that it can actually make them pass through a focal point, or at least near it. All right. Now, with a little bit of geometry, we can show that this focal point, let me put this in green. Let me go with a darker green here. Whoops. Let me pick a color like this. Okay. So this focal point here, if I take this distance from where the backside of the mirror is, okay, or where the vertex of the mirror is, I should say, out to the focal point, it should be the radius over 2. All right. So the focal point is at half the radius of curvature of the mirror. So if we have a radius of curvature of r, the focal point will be approximately at r over 2. In the ideal case, it would be exactly at r over 2, but it's pretty close to that. Okay, so that's a property of the spherical mirror. All right, now that's for a concave mirror. So we just looked at the concave case. Let's look at the convex case. So let me draw in the optical axis, and I'm going to start my mirror right here. All right. Now this time the focal point, it's going to curve the other way. So it's going to curve something like this instead. All right, and we could put in radii. Whoops, that's not a very good one. Angle this better so I can put in some radii. They're not very straight, but you can use your imaginations and pretend they are. So there are some radii. Now, the radii are, we said they're the normal lines. We could extend those beyond the mirror to see what the normal lines would look like. So what's going to happen with light rays coming into this mirror? It's clearly not going to focus them. It's going to scatter them instead, all right? But something interesting will happen. The light rays, and if you have one coming down the middle, it will just go in and reflect the same way. But if you had a light ray hitting the mirror there, it will reflect so that it is perpendicular. I'm sorry, so the angle of reflection is the same as the angle of incidence, and it does something like that. The same thing would happen up here, the light coming in. This is coming in parallel to the optical axis. So it's as if it's coming from infinitely far away. It would reflect something like that. Now, from what we learned about two mirrors, if we were to walk around this thing and we had an eye here, and we either move or we have a second eye over there. People have two eyes usually. We would be able to locate the focal point back here. Now let me actually change colors for that. We don't actually have light meet back here, but it's as if the light bouncing off of the mirror had come from that point. And we could do the same thing for rays that are further out. So if I had rays, let me change back to red for my light rays. So if I had a light ray here, it would reflect something like this. And this is a spherical mirror, not a parabolic mirror. If it were parabolic, we would see that, oh, I should switch to green here. It would appear to be coming from roughly the same point. If it's a spherical mirror, it won't be exactly right, but it'll be close. All right, and that would look something like this. And you can see, oh, that's also coming away from the same point. So the light rays don't actually come from this point, back here, the green point, but they appear to be coming from that point. So it's almost like we have a virtual focal point. We don't say that it's a virtual focal point, but what we do say is This distance, once again, from the mirror to where the focal point is r over 2. So in the top case, we say that the focal length f, usually we use f for that. You should probably check to see which, yes, your book does use that, is r over 2. In this case, we say that we have a negative focal length. So we say that the focal length is, actually maybe it's still r over 2, but it's a negative radius of curvature. So this gives us a negative focal length. When we get to the formulas for reflections, we will be able to, where we can compute where an image will form. We have to remember that when we have a convex mirror, let me write that this is convex. When we have a convex mirror that makes the light spread out instead of converging, we have a negative focal length that causes the light rays to spread out.